Okay, in this short video what we're going to look at is the fundamental accounting principle. So as you can see here, this is part of our organized counting unit. So it's a field of combinatorics. It's the study of organized counting when working with complex situations. So in some ways we're going to be making some charts and some tree diagrams and just other ways of solving problems, as well as today we're going to learn a very simple technique for calculating the number of ways or number of possible outcomes of certain events. So we'll learn a really nice simple way to solve these problems. We'll start out by looking at it as tree diagrams, and then we'll talk about how that can extend for more complex problems and how we can solve it mathematically. So the fundamental accounting principle is something we've already looked at technically in some of the other work that we've done when we talked about probabilities and possible outcomes in certain events. So we're just going to continue with that and just come up with this new principle that we can use. So let's say that you go into your closet and you want to make an outfit, and inside your closet, for whatever reason, you only have a white shirt and a blue shirt. You also have brown pants, green pants, and purple pants. So basically the question is, how many outcomes are there if you went in and you randomly picked a shirt and randomly picked a pair of pants to put on? So we'll start with drawing a tree diagram to show us the number of outcomes, and then we'll see how we can do this in a slightly different way. So the first option you have when you reach in is to grab a white shirt or a blue shirt. So I'll call it white shirt, blue shirt, like this. Next, you have an option for 3 different pairs of pants. You can have brown, green, purple. Brown, green, or purple. So now what you'll see, if you look at the number of possible outcomes here, there are 6 outcomes that you could have. Again, we've sort of already looked at this before. Another way to think about this, if we want to get to the number 6, is just to say to yourself, alright, how many options were there for the shirt? Well, there were 2 options. So I use that line just to show me the number of options, since we're picking a shirt and a pair of pants. So this is our shirt, and this is the pants. And we multiply, and there were 3 options for the pants. So there were 2 options for the first part, 3 for the pants, which gives us a total of 6 possible outcomes. Alright, seems pretty straightforward. Let's look at another option here. Let's say you want to flip a coin and then roll a single-sided die. A single 6-sided die, sorry. So what we do is we take a coin, and the first time you flip it, you could get heads or you could get tails. And then from here you can get the numbers 1, 2, 3, 4, 5, or 6. 1, 2, 3, 4, 5, or 6. Okay. How many possible outcomes are there in this case? There were 2 branches that each branched off to 6. So we have 6, and we get 12 different outcomes. Okay, using the technique above, we could say how many options were there for the coin and how many options for the die. Well, there were 2 options, head or tails, for the coin. For the die there were 6. 2 times 6 is 12 possible outcomes. Drawing tree diagrams is helpful. It's good for visualizing. You can see how many have where you get a head first and then a 6, so you can figure out probabilities very easily. The one issue with them is that they get quite large quite fast, and if we start getting into really complex problems, drawing a tree diagram is not going to be helpful at all. So let's take a look at some possibilities here. So you'll need a calculator for these types of problems for sure. So let's say that you want to flip a coin, roll a single-sided die. Now this should be a single 6-sided die. Otherwise you'd be there's no such thing as a 1-sided die. And a spinner with 4 equal sections. Without using a diagram, obviously I didn't give you enough space because I don't want to go head, tails, 6 different options, then off those 6 draw another 4. That's just crazy to figure out how many possible outcomes there would be. So for the coin, and then the die, and then the spinner, we look at the number of options. The coin is head or tails, the die has 1, 2, 3, 4, 5, or 6, and so there's 6 options, and then the spinner had 4 equal sections, like so, and what you end up with is 12 times 4, or 12 times 2, sorry, 24 times 2, which is 48 outcomes. So there's 48 outcomes that could come from this. So if you'd drawn the tree diagram, you would have had 48 branches at the very end. It would have went from 2, and each of those 2 would have split to 6, and each of those 6 for each of those other ones would have branched off into 4 to give a total of 48 outcomes. Much easier to do it using this fundamental counting principle. Alright, randomly select a number between 1 and 100 and a letter from the alphabet. Okay, well, this is the number between 1 and 100 and the letter of the alphabet. Well, 1 to 100, so that's going to be, you have 100 options there, and then the letter, there's 26 letters in the alphabet, and you end up with 2600 outcomes. Quite a few. You do not want to draw this out, drawing like branch 1 and then 26 coming off of it, 2 with 26 coming off of it. You'd have 2,600 branches at the end that you'd have to deal with, which would not be ideal. Alright, you roll a standard die, which is a 6-sided die. How many possible outcomes are there to roll how many possible outcomes are there for 2 rolls, 3 rolls, and 8 rolls? Well, roll number 1, roll number 2. So roll number 1, you have 6 options and 6 options. Now, because it's the same, we can actually go 6 squared, and that's 36. So for B, 3 rolls, 1, 2, 3, is 6 options each time, and so that's basically 6 cubed, 216 possible outcomes. Okay, and then it says 8 rolls. Now I'm not going to bother drawing out all 8 outcomes here, but I'm going to do 6 to the power of 8. So since it would be 6 times 6 times 6 times 6 times 6, so 6 to the exponent 8 is 1679616. So it's a quite large number. It's 1,679,616. Okay. Let's say you're asked to make a password consisting of only 6 letters. Okay, calculate the number of different passwords if A, repetition is allowed. Alright, so if repetition is allowed, and there's 6 letters, that's 1, 2, 3, 4, 5, 6, and we look here and repetition is allowed, we do multiplication, like so. There are 26 letters, 26 letters, 26, 26, 26, 26, or it's just really 26 to the power of 6. So 26 to the power of 6 is a large number. Like that. And it's a very, very big number. Now let's say this password and there's no repetition allowed. Well, if there's no repetition allowed, the first option you have 26 possible letters to pick from, but the next time, since you've used one of them, there's only 25 left. So 26 times 24 times 23 times 22 times 21, and so that's 26 times 25 times 24 times 23 times 22 times 21, which is 165765600, like so. Did I write that down correctly? Yes. So there's fewer than there was if you were allowed to repeat them. And you can see that this is 308 million-ish, and this is 165 or 166 million-ish. So clearly less. So this is what it looks like when you can't repeat. They drop by 1 each time. Okay, I think you get the hang of it now. You can probably finish this off without having to watch this video, but I'll continue along just to help you out. Let's say you have a password that can only consist of six characters, but the characters can be either a letter of the alphabet or a digit from 0 to 9. calculate the number of different passwords if A, repetition is allowed, and if not. So if repetition is allowed, it says that we can use either a letter of the alphabet, so there's 26 letters, and there are 10 digits, 0 to 9. That's a total of 36 options. So it's 36 to the power of 6. Now another way to do it is 36 times 36 times 36 times 36, but you get the idea that if it's 6 characters long and there's 36 options for each, then it's simply this massive number of 2, 1, 7, 6, 7, 8, 2, 3, 3, 6, which is that 2 billion-ish different outcomes are allowed in this case. For B, if repetition is not allowed, there's 36 for the first choice, but then you've lost one. So it's 35, 34, 33, 32, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6. So we go 36 times 35 times 34 times 33 times 32 times 31, and there's a lot but fewer when we see this. So it's 410,240, like so. Only about a billion. So just under half, I guess. Sorry, just a bit over half. Okay, so the last one that we have here is we're selecting a delegate group from your class to represent you in a district meeting. There are only 3 positions available, and there's 31 people in the class. How many possible ways could you select the group? 1, 2, and 3. Okay, so there's a group of 3 people that we're picking, and obviously once we pick someone, they're off. They're not in the classroom anymore. So the very first one that we get is 31, and then that's the first person in the group. The next person in the group, there's only 30 people left to pick from, and the last one, 29. So it's 31 times 30 times 29 is 26,970 different delegations you could send, or delegates, groups that you could send. And that's a lot. That's a very big number compared to the other, when you think about it at first bit. So the definition down here is the fundamental counting principle, which basically says that if the first action can be performed in m ways, and a second in n ways, and a third in p, and so on and so on and so on, then if you just have to multiply the different number of ways that each of them can happen to get the answer. Now what you'll notice here is that this is the word and often implies multiplication, whereas if you think about before, or tended to represent the addition of things. So that was the union of a set, and this is more of like that intersection. And so and is going to be this fundamental counting principle, and we're going to use multiplication, and or is when we would use addition. So what you're going to do from this point is to work through the problem set that's provided, and then we're going to post a select grouping of questions from this other from the textbook. And so you're going to work through this first part and then through the textbook questions. They get quite complex at times, but if you follow the procedure carefully and follow the steps I just went through, shouldn't be a problem.